Hello, everyone. As I promised in last session, I'm gonna review example 2.3 in the slides we had last week. As you see, here we have sort of spring assemblages, but it's a little bit different from the previous examples since we have three springs and the left one has K1 as the spring constant. This has K2 and K3. This is K1. But we have a sort of solid plate here, which forces all of these nodes to deform in horizontal direction. As you remember, I said for the springs, we only have uh, deformations along 1 degree of freedom, which is horizontal. I mean, not every time horizontal. I mean, the direction of the spring, whatever it is. If the spring is vertical, so the deformation will be vertical. But in this case, all of the springs are horizontal, so the deformations will be only horizontal. And as you see, this solid plate, which connects these three nodes together, will force the end of the spring, the left spring, and the right hand side of the left spring and the left hand side of the right springs, all of them will move horizontally. So that's why when you want to number the nodes, this node is number one, and we put number two for all these nodes because they will deform the same. They're not different in deformation along the horizontal axis. And you have number three and number four. So you have altogether four nodes and you have three elements. Element number one, element number two, and element number three. And obviously for the support conditions, D1 is 0 and D3 and D4 are 0, and only the deformation in the node number 2 is free to move. And you can say deformation at node number 2 for element number 1, 2, and 3 are the same and identical to D2x, for example. So to solve this problem, you need to assemble the stiffness matrix for every individual element and then assemble the whole structures matrix as we have done this for all the previous examples. Here we are with the stiffness matrix for element number one, which is K1 minus K1 minus K1 K1. As you know, for element number two and for element number three. So we have three elements and three small stiffness matrices, each for one element. And the global stiffness matrix will be something 4 by 4 because we have four nodes, 4 degrees of freedoms, and you can draw some sort of empty matrix for yourself as we practice during the lecture and number 1, 2, 3, 4 like a line, hint line, and here 1, 2, 3, 4 as a hint for yourself, and start to bring all of those numbers to the right place in the global stiffness matrix. So if you do so, I've tried to put the numbers with different colors. For example, for element number one, I use blue color. For element number two, I use red color. And for element number three, I used green color. And you can see each number is coming from which matrix. So this will be, the other cells are 0, which you don't see anything. These are 0. And this is the whole matrix of the structure. And as you know, we need to apply the boundary condition for this matrix. And we have three boundary conditions, as you see in node number one, node number three, and node number four. They are connected to supports, to the walls, and we need to eliminate rows and columns corresponding to those degrees of freedoms. That's why you need to eliminate rows and columns of number 1, 3, and 4. And if you do so, this is the general form of the stiffest matrix relating the deformations to the forces. And as you know, these three, F1, F3, and F4, they are support reactions. And this P is the external force at node 2. And on the other hand, D1, D3, and D4, they are all 0, and D2 is unknown. That you should calculate it. So for that purpose, for the applying of boundary conditions, you eliminate row 1 and column 1, row 3 and column 3, and row 4, column 4. What will be remained is P equal to this term multiplied by D2x. And simply you can calculate D2x equal to P divided by the summation of K1, 2, and 3. And if you calculate D2x, you have all the unknown deformations, and you can put everything in this vector and multiply by this matrix, and you will come up with all the support reactions you need. And consequently, you can calculate internal forces in each spring by using those individual small individual matrices for all the elements. This is the example number 2, 3 of the book, and I will inform all the students with an email that I've also released. I will release a tutorial for you to be solved, and after a few days, probably on Thursday, I will reveal the solution, and you can compare your solution with the correct solution. I hope you have learn something from this video, and see you all on Friday. So I just try to